Welcome to another edition of Coonrod's Corner. Today's topic, Rogers microwave circuit materials with high thermal conductivity. Now here's your host, John Coonrod.
Hello, welcome to Coonrod's Corner. My name is John Coonrod. I am a technical marketing manager for Rogers Corporation. Today I'm going to spend a few minutes to talk about microwave circuit materials with high thermal conductivity. Now in the past I have done a Coonrod's Corner, a short video on a subject that's similar, and that was titled Thermal Management of Microwave PCBs. This particular talk today is going to be somewhat related, but mostly geared toward materials only. Even though to begin with, I do need to talk about how the materials are used in circuit form. And with that, let's go ahead and get started. The picture shown here in the upper left is right out of a Physics 101 textbook, and it's a very simple way to think about heat flow. And what it's shown is a hot reservoir and a cold reservoir that's connected together by a thermal conductor, and the heat will flow from the hot reservoir to the cold reservoir. That's just a very simple heat flow model. The formula for that is shown to the right, and then below is how you apply this to the printed circuit board technology. And what's shown here below is a microsectional view of a microstrip transmission line circuit that is bonded to a heat sink. So basically we're going to assume that the signal plane is generating heat, so that's the hot reservoir, and that we assume that the cold reservoir is the ground plane, and that's at the same thermal potential as the heat sink that it's bonded to. And then the heat flow is going to flow through the material itself, through the dielectric material, so the material itself is going to act as the thermal conductor. Now, if you want to improve heat flow, which is the desire for thermal management, you want to increase heat flow, which means H has to be higher in the formula. So one way to do that is to make L smaller, and L is the thickness of the laminate, so a thinner laminate basically makes the heat flow increase, which is true. Another thing you could do is increase K, so K is directly proportional to H. If you increase K, which is thermal conductivity, that's also going to increase heat flow. There are two types of thermal management scenarios. Actually, it's a little more complicated than that, but just for keeping it simple today, we want to talk about just these two scenarios. And one is device heating and the other is trace heating. Device heating is when an active device is placed onto a circuit and the circuit needs to deal with the thermal management of the device actually heating the circuit. Trace heating is when the trace of the circuit itself is being heated by applied RF power. So I've shown a very simple drawing here of these two different scenarios just to explain them in a little more detail. So as can be seen in the drawing here, the drawing on the left is the same circuit again. It's a microstrip transmission line bonded to a heat sink, and then on top of it is an active device generating heat. And there's some of the heat that's being radiated off, and then some of the heat is in direct contact with the signal plane, so that means the heat has to transfer from the signal plane to the ground plane down to the heat sink below. And that's one scenario for thermal management. Another scenario for thermal management is RF trace heating, and that's the picture shown to the right. And that is when RF power is applied to a conductor and the circuit will heat up due to the losses of the circuit with the applied RF power. And essentially, when RF power is applied to the circuit, however lossy the circuit is, that's how much heat's going to be generated. A more lossy circuit, higher heat generation. In the case of what's important for materials for these two different scenarios, one of them is pretty simple, and that's the case of the device heating. The device heating really is looking at material properties that are simply the thickness of the substrate and the thermal conductivity. The thermal conductivity, of course, being higher is an important thing, and the thickness substrate being thinner is an important thing for increasing heat flow. In the case of material properties for trace heating, it's a little different. You still have the issue of the substrate thickness and also thermal conductivity, of course. However, now you have some of the RF issues that come into play. Now we have dissipation factor and copper surface roughness. Dissipation factor can increase the dielectric losses, and the copper roughness can also affect the conductor losses. And in both cases, these losses, if they increase, then it's going to cause more heat to be generated when RF power is applied. Now, how the heat actually moves from the signal plane to the ground plane may not be as simple as you might think. Of course, what you want is a direct line of pass straight through from the signal plane straight down to the ground plane where the heat sink is below. But in some cases, due to the formulation of the materials, that could actually be a little different, and you can get some heat spreading away from that direction into the XY plane, which is really not desired. What I'm showing here is a cross-sectional view of a material that is used in the high-frequency industry, and really what it is a woven glass ceramic-filled PTFE laminate. And you can imagine the top signal plane being on the top layer, obviously, and the bottom ground plane on the bottom of this picture. And ideally, the heat should flow from the top to the bottom. But you can also see by the numbers of the different materials that make up this substrate, the numbers of thermal conductivity are very different for the different components that make up the substrate. And in some cases, especially true with the glass layer that's actually there for mechanical support, that actually has a very high thermal conductivity, and that can cause heat spreading. So instead of the heat going from the top to the bottom straight through, once it hits that glass layer, it could actually spread out to the XY plane. And heat spreading is generally not desired. You usually want the heat to go directly from the signal plane to the ground plane and effectively to the water-cooled heatsink or whatever type of heatsink it is that's attached to the ground plane. The PCB substrates that are used in the industry really are not that good a thermal conductor, even though they're behaving functionally as a thermal conductor to transfer heat from the signal plane to the ground plane. If you actually look at the numbers for thermal conductivity, they're typically around 0.2 or 0.3 watts per meter Kelvin. And that's really not that good. Considering copper is about 400, most of our substrates are considered as thermal insulators, but they have to act like a thermal conductor. So in some cases, we have formulated our materials to be increased thermal conductivity, and typically, as a rule of thumb, when a material has a thermal conductivity of 0.5 watt per meter K or greater, that's considered very good thermal conductivity. So I've put together a table of information that gives a highlight of some of the materials used in the high-frequency industry where thermal management can be a concern. The table of information shown here is a combination of materials that are used in the microwave world for any type of applications that are high power or thermal management in general. And I do have the high TG FR4 in here, and even though that's not a microwave material, many times it's used in combination with high frequency materials as a hybrid multilayer, and knowing the thermal conductivity can be important. In this case, I've estimated the thermal conductivity to be 0.25 watt per meter K, and it really depends on the type of FR4 that you're looking at. Some are a little better, some are a little worse, but the 0.25 watt per meter K is a pretty good number in general. And then if you look at the nearly pure PTFE laminate, you can see the dissipation for that material is extremely good at 0.0008. That really is not going to generate much heat when RF power is applied to it. However, the drawback is when heat is generated, it's not going to come out of the circuit very easily because the thermal conductivity is so low at 0.2 watt per meter K. Now the answer to that really is a material that has both attributes, and that is the RO3003 substrate. That material has a dissipation factor very close to the PTFE at 0.001, which is considered extremely low loss. So it's not going to generate too much heat when RF power is applied to it, and it also has thermal conductivity that's very good at 0.5 watt per meter K. Now some of the other materials on here are often used in high power applications. The RO4835 and the RO4360G2 substrates. These are non-PTFE materials that are very often used in high layer counts, and they, as you can see, they have low loss at dissipation factor of 0.0037, 0.0038, and even more importantly is the thermal conductivity is actually very outstanding at 0.62 for the 4835 material and 0.8 for the 4360G2 materials. Now also the TC350 and the TC600 materials, these have been used a lot in the industry and being used a lot today for high power applications or any applications where thermal management is an issue. And you can see why here. The thermal conductivity for both of these materials is very good at 0.75, and 1.1 is considered extremely high thermal conductivity. And both of them have dissipation factor that is low, so you have very low losses due to that at 0.002. Now the ultimate material for thermal management would be the RT Daroid 6035 HTC laminate, and you can see why here in the table that the thermal conductivity is outstanding at 1.44 watt per meter K, and the dissipation factor is very low at 0.0013. So basically what happens when RF power is applied to a circuit with this material, there's not much heat generated in the first place, and whatever heat is generated is taken away very effectively by this very high thermal conductivity. This concludes this session of Coonrod's Corner. Thank you for watching.
For additional information and technical tools, if you're not already a member, join the Rogers Technical Support Hub and gain access to calculators, technical papers, and more Rogers Corporation informational videos. Rogers Technical Information is also available at your fingertips with the Rog mobile app, available for the iPhone, iPad, and Android devices. Check it out today.